In the depths of space, something invisible is working to tear our universe apart, atom by atom. Right now, as you watch this video, a mysterious force comprising 68% of everything that exists is stretching the fabric of reality at an accelerating rate. This cosmic phantom grows stronger with each passing moment, and if current observations prove correct, it will eventually overcome every force that holds matter together. Scientists call this the Big Rip scenario, and it represents the most violent possible ending to our cosmic story. Forget gentle heat death or gradual cooling over trillions of years. We're talking about a universe that literally shreds itself into nothingness, ripping apart galaxies, solar systems, planets, molecules, atoms, and even the fundamental particles that make up reality itself. The timeline for this cosmic destruction spans just 22 billion years from now, which sounds like forever until you realize that's only about twice the current age of our universe. But here's what makes this scenario truly disturbing. Recent observations from the most advanced cosmic surveys ever conducted suggest that dark energy, the mysterious force driving this potential catastrophe, might actually be growing stronger over time. The Dark Energy Spectroscopic Instrument has detected hints that our universe's fate could be far more violent than anyone previously imagined. These findings have shaken the foundations of cosmology, forcing scientists to confront the possibility that we live in a phantom energy universe destined for complete annihilation. If you're fascinated by cosmic mysteries that challenge everything we think we know about reality, hit that like button and subscribe, because what I'm about to reveal will fundamentally change how you see the universe around you. We're going to explore the cutting-edge science behind dark energy, examine the latest observational evidence, and walk through the terrifying timeline of how our cosmos might end in the most spectacular destruction imaginable. The story begins with one of the most shocking discoveries in the history of astronomy. In 1998, two independent research teams studying distant supernovae made an observation that defied every expectation about cosmic evolution. Instead of finding that the universe's expansion was gradually slowing down due to gravitational attraction, they discovered something impossible. The expansion of space itself was accelerating, driven by an unknown force that seemed to push against gravity on the largest scales imaginable. This discovery earned the Nobel Prize in Physics and introduced humanity to dark energy, the most mysterious component of our cosmos. Dark energy doesn't emit light, doesn't interact with ordinary matter through electromagnetic forces, and remains completely invisible to every instrument we've ever built. Yet this phantom substance comprises more than 2/3 of everything that exists, making it the dominant force shaping cosmic evolution on scales larger than galaxy clusters. Understanding dark energy requires grasping one of the most counterintuitive concepts in physics. While ordinary matter becomes less dense as space expands, dark energy maintains constant density throughout cosmic growth. Picture a balloon filled with air. As you inflate the balloon, the air inside becomes less dense because the same amount of matter now occupies a larger volume. Dark energy behaves completely differently. As space expands and creates more volume, dark energy density remains exactly the same, which means the total amount of dark energy in the universe continuously increases. This bizarre behavior creates what physicists call a positive feedback loop. More space means more dark energy, which drives faster expansion, which creates even more space, which generates additional dark energy. The process accelerates exponentially, like a cosmic avalanche that grows more powerful with each passing moment. But the truly terrifying possibility emerges when we consider what happens if dark energy becomes even more exotic than scientists initially believed. The key to understanding our cosmic fate lies in a single number called the equation of state parameter, represented by the letter W. This parameter measures the ratio between dark energy's pressure and its energy density. When W equals exactly -1, dark energy behaves like Einstein's cosmological constant, providing steady acceleration that never grows stronger over time. This scenario leads to heat death, where the universe gradually cools and dilutes over countless trillions of years until stars burn out and black holes evaporate, leaving behind cold, empty space approaching absolute zero temperature. But when W drops below -1, we enter phantom energy territory where the rules of physics become truly nightmarish. Phantom energy violates fundamental assumptions about how energy and matter should behave, creating a universe where the expansion rate doesn't just accelerate, but where acceleration itself accelerates. The expansion becomes runaway, unstable, and ultimately catastrophic as it overwhelms every force that holds structures together across cosmic scales. Recent observations have detected subtle hints that dark energy might indeed be evolving toward phantom energy behavior. The Dark Energy Spectroscopic Instrument, which uses 5,000 robotic fibers to simultaneously observe thousands of galaxies across vast cosmic distances, has created the most detailed three-dimensional map of the universe ever constructed. This revolutionary survey measures how galaxies move through space by analyzing the redshift of their light, revealing how cosmic expansion has changed over the past 11 billion years. The initial results from this cosmic census sent shockwaves through the astronomical community. Instead of finding constant dark energy as most theories predicted, the data suggests that dark energy has been weakening over cosmic history, with its influence decreasing by several percent since the universe was young. This finding achieves statistical significance levels that would be considered definitive proof in most scientific contexts, with confidence exceeding 99.9%. If confirmed by future observations, this discovery would represent the first real clue about dark energy's nature in 25 years since its original discovery. The implications extend far beyond academic curiosity because weakening dark energy could indicate a transition toward phantom energy behavior. Some theoretical models predict that dark energy might undergo phase transitions, similar to how water changes from liquid to gas, potentially shifting from constant cosmological constant behavior to phantom energy dynamics. The mathematics behind phantom energy reveal why this scenario terrifies cosmologists. In a phantom energy universe, the total energy content increases without bound, seemingly violating conservation of energy through mechanisms that operate outside our current understanding of physics. The expansion rate grows exponentially, creating what mathematicians call a finite-time singularity, where physical quantities become infinite in a measurable period, rather than asymptotically approaching infinity over unlimited time. Computer simulations of phantom energy universes reveal a timeline of destruction that unfolds with mathematical precision. The process begins slowly, affecting the largest and most loosely bound structures first. Galaxy clusters, held together by relatively weak gravitational forces across millions of light years, would be the initial casualties as phantom energy's influence grows strong enough to overcome their binding energy. Individual galaxies with much stronger internal gravitational fields would survive longer, but eventually succumb as the expansion rate continues accelerating. The progression follows a strict hierarchy determined by gravitational binding energy. Structures with weaker gravitational bonds disintegrate first, while more tightly bound systems persist longer before reaching their inevitable breaking points. This creates a countdown of cosmic destruction that proceeds from the largest scales down to the smallest, with each level of organization failing as phantom energy overwhelms the forces that maintain structural integrity. But the Big Rip scenario involves more than just gravitational effects. As phantom energy grows stronger, it begins affecting the fundamental forces that operate on smaller scales. The electromagnetic force that binds electrons to atomic nuclei, the strong nuclear force that holds protons and neutrons together, and even the interactions between quarks within individual protons would all fail as the cosmological horizon shrinks below their characteristic scales. This represents a complete breakdown of physics as we understand it. The concept of cosmological horizons becomes crucial because it determines what parts of the universe can still communicate through fundamental forces. In normal cosmic expansion, distant galaxies gradually disappear beyond our cosmological horizon over hundreds of billions of years. However, in a phantom energy universe, this horizon shrinks catastrophically as expansion accelerates without bound. The shrinking horizon creates islands of causally connected space that become increasingly smaller, eventually reaching scales comparable to individual star systems, planets, and ultimately atoms. Forces that require information to travel at light speed or slower can no longer maintain connections across expanding space. When the horizon shrinks below the distances these forces must traverse to hold matter together. Current measurements place the equation of state parameter very close to -1, but statistical uncertainties leave room for phantom energy behavior. The precision required to definitively rule out the Big Rip presents one of the greatest challenges in observational cosmology. Multiple independent techniques must converge on measurements accurate to within a few percent to distinguish between constant dark energy and phantom energy scenarios. The latest consensus from combining different observational methods suggests W equals -1.013, with uncertainties that still permit phantom energy values. While this measurement remains consistent with constant dark energy, it also allows for the gradual transition toward phantom energy that could culminate in the Big Rip. Future surveys promise dramatic improvements in precision, but the fundamental question of our cosmic fate remains tantalizingly unresolved. The theoretical challenges surrounding phantom energy highlight gaps in our understanding of fundamental physics. Phantom energy appears to violate the dominant energy condition, a principle that ensures energy density remains positive and greater than pressure throughout space. This same condition helps prevent exotic phenomena like traversable wormholes, faster-than-light travel, and time machines by maintaining consistency in Einstein's general relativity. If phantom energy exists, it suggests that our universe operates according to physics beyond current theoretical frameworks. Some proposals invoke quantum field effects, modified gravity theories, or interactions with higher dimensional spaces, but all these possibilities remain highly speculative without empirical support. The apparent violation of energy conservation during phantom energy domination poses additional conceptual challenges that might require revolutionary advances in theoretical physics to resolve. Despite these difficulties, the precision of modern observations demands that scientists take phantom energy seriously as a possibility. The data collected by surveys like the Dark Energy Spectroscopic Instrument continues pushing the boundaries of what we can measure about cosmic expansion, bringing us closer to definitive answers about our universe's ultimate destiny. Each new measurement refines our understanding of dark energy's properties and helps determine whether we live in a cosmos destined for gentle heat death or violent disintegration. The observational evidence supporting phantom energy scenarios becomes more compelling when we examine the acceleration mechanism that would drive cosmic destruction. Unlike normal dark energy that provides steady acceleration similar to a car maintaining highway speed, phantom energy creates runaway expansion where the acceleration itself continuously increases. Picture a vehicle whose accelerator pedal grows progressively heavier, forcing ever greater speeds until control becomes impossible. This acceleration operates through pressure-energy relationships embedded within Einstein's field equations, where phantom energy's extreme negative pressure generates increasingly powerful, repulsive gravitational effects. As space expands, additional phantom energy materializes in the growing volume, driving faster expansion that creates even more space and thus more phantom energy. This positive feedback loop represents an inherently unstable system that mathematically guarantees infinite expansion rates and energy densities within finite time periods. The timeline for this cosmic catastrophe has been calculated with disturbing precision, using phantom energy parameters that remain consistent with current observational constraints. Researchers have mapped the progression of universal destruction across 22 billion years. The scenario begins with galaxy clusters becoming gravitationally unbound approximately 200 million years before the final moment. These massive structures, containing thousands of individual galaxies held together across millions of light years, would simply drift apart as phantom energy overwhelms their collective gravitational binding. Individual galaxies would survive this initial phase but face their own destruction roughly 60 million years before the Big Rip. The Milky Way, Andromeda, and every other galactic island would lose cohesion as their spiral arms unwind, and their central supermassive black holes can no longer anchor surrounding stellar populations. Billions of stars would scatter into the expanding void, their planetary systems intact but isolated in an increasingly hostile cosmic environment. Solar systems represent the next level of destruction, maintaining stability until approximately 3 months before the final catastrophe. Earth's orbit around the Sun would remain stable through galactic dissolution and even the initial phases of phantom energy dominance. But as the expansion rate reaches critical thresholds, gravitational bonds holding planets to their stars would snap like overstretched rubber bands. Earth would fly off into space along with every other world, carrying its cargo of life into the cosmic deep. The final stages of destruction unfold with breathtaking speed. Stars themselves would be torn apart in the last minutes as phantom energy overcomes nuclear forces maintaining stellar integrity. The sun would disintegrate not through fuel exhaustion or gravitational collapse, but through space expanding so rapidly that nuclear fusion reactions can no longer hold stellar cores together. Every star in the observable universe would suffer the same fate simultaneously. Planetary destruction follows within moments. Earth would lose its spherical shape as phantom energy stretches space faster than gravitational forces can maintain our world's structural integrity. The process wouldn't resemble an explosion or collision, but rather a gradual stretching that accelerates beyond imagination. Mountains, oceans, continents, and everything familiar about our planet would elongate and separate as space itself expands beneath them. Molecular bonds represent the next casualty in this hierarchy of destruction. The electromagnetic forces that hold atoms together in complex molecules would fail as space expands faster than electrical interactions can propagate. Water molecules would dissociate into individual hydrogen and oxygen atoms. DNA strands would unravel as the chemical bonds maintaining genetic information snap under the strain of accelerating expansion. Every biological process would cease not through death, but through the fundamental inability of chemistry to function in rapidly expanding space. Individual atoms face destruction approximately 10 to the negative 19th seconds before the Big Rip. Electrons orbiting atomic nuclei would lose their quantum mechanical binding as space expands faster than electromagnetic forces can maintain atomic structure. Hydrogen, helium, carbon, oxygen, and every other element would cease to exist as coherent atoms, leaving behind isolated protons, neutrons, and electrons scattered throughout space. The final moment arrives when atomic nuclei themselves disintegrate. The strong nuclear force, which binds protons and neutrons together with incredible strength across distances measured in femtometers, would finally succumb to phantom energy's relentless assault. Every atomic nucleus in the universe would simultaneously decompose into individual quarks and gluons, the most fundamental particles known to physics. But even this represents only the penultimate stage of destruction. Theoretical models suggest that phantom energy might overcome the forces holding quarks together within protons and neutrons, reducing matter to its most elementary components. The universe would become a sea of isolated particles expanding at infinite rates through space stretched beyond any meaningful measurement. The concept of cosmological horizons becomes crucial for understanding how phantom energy achieves this complete destruction. Every location in space has an associated horizon that defines the maximum distance from which information or forces can arrive. Light travels at finite speed, so forces that depend on electromagnetic interactions cannot influence matter beyond the distance that light can travel during relevant timescales. In normal cosmic expansion, these horizons grow larger over time as light has longer periods to traverse cosmic distances. But phantom energy reverses this process, shrinking horizons as expansion accelerates beyond light speed across increasingly smaller scales. When the horizon becomes smaller than the distance separating components of any structure, fundamental forces can no longer hold those components together. Galaxy clusters lose cohesion when their horizons shrink below cluster scales spanning millions of light years. Individual galaxies disintegrate when horizons contract below galactic dimensions of hundreds of thousands of light years. Solar systems fail when horizons drop below astronomical unit scales. Planets lose integrity when horizons shrink below planetary radii. Atoms decompose when horizons contract below atomic scales measured in angstroms. This horizon shrinkage represents causal disconnection on a cosmic scale, where different parts of previously unified structures can no longer exchange information or forces. The electromagnetic field binding an electron to a proton requires constant communication across atomic dimensions. When expanding space prevents this communication, the atom simply ceases to exist as a bound system. The mathematical description of phantom energy reveals why this scenario violates intuitive expectations about energy conservation. In normal physics, total energy remains constant even as it transforms between different forms. But phantom energy appears to create new energy from nothing as space expands, with the total energy content of the universe increasing without bound throughout the Big Rip process. This apparent violation occurs because phantom energy's negative pressure performs more work than its positive energy density contributes to cosmic dynamics. The net effect resembles a cosmic perpetual motion machine that generates unlimited energy through expansion itself. Theoretical physicists struggle to reconcile this behavior with fundamental conservation laws, leading some to question whether phantom energy represents physically possible behavior or mathematical artifacts of incomplete theories. Alternative explanations invoke exotic physics beyond current understanding. Some proposals suggest phantom energy might draw power from higher dimensional spaces or parallel universes through mechanisms that preserve energy conservation when viewed from broader perspectives. Others invoke quantum field effects operating at cosmic scales, where virtual particle creation and annihilation might generate phantom energy through processes invisible to current observational techniques. Modified gravity theories offer another potential explanation, suggesting that Einstein's general relativity might require corrections at the largest cosmic scales. These modifications could produce apparent phantom energy behavior without requiring exotic matter or energy sources. However, all proposed modifications face the challenge of preserving general relativity's remarkable success in describing gravitational phenomena across smaller scales while explaining phantom energy effects at cosmic dimensions. The observational techniques used to detect phantom energy behavior rely on measuring cosmic expansion across vast distances and time periods. Type Ia supernovae serve as cosmic lighthouses because they achieve consistent peak brightnesses regardless of their host galaxies, allowing astronomers to determine distances by comparing apparent brightness with known intrinsic luminosity. These stellar explosions provide snapshots of cosmic expansion rates at various epochs throughout universal history. Baryon acoustic oscillations offer complementary measurements by detecting characteristic scales imprinted in galaxy distributions by sound waves that propagated through the early universe. These acoustic signatures create standard rulers that appear consistently across cosmic history, revealing how space has expanded since the universe became transparent to light approximately 380,000 years after the Big Bang. The cosmic microwave background radiation provides a third independent constraint by preserving information about universal geometry and composition from when space first became transparent. This ancient light carries subtle patterns that encode details about dark energy's properties and evolution over cosmic time. Combining measurements from all three techniques provides the statistical power needed to distinguish between different dark energy models and determine whether phantom energy behavior represents reality or observational artifact. Current data suggests phantom energy remains a genuine possibility despite theoretical challenges and observational uncertainties. The equation of state parameter continues hovering near the critical threshold that separates constant dark energy from phantom energy behavior. Future observations will refine these measurements, potentially resolving the question of our cosmic fate within the next decade as survey precision improves and systematic uncertainties decrease. The implications extend far beyond academic curiosity because phantom energy would fundamentally alter our understanding of physical reality. The violation of energy conservation and dominant energy conditions would require revolutionary advances in theoretical physics, potentially opening pathways to exotic phenomena previously considered impossible. Traversable wormholes, faster-than-light communication, and time travel might become theoretically possible in universes where phantom energy operates according to unknown physical principles. But these speculative possibilities pale beside the existential implications of living in a Big Rip universe. Every achievement of human civilization, every work of art, every scientific discovery, and every moment of love or joy would face inevitable erasure as phantom energy tears apart the atomic foundation of existence itself. The timeline spanning 22 billion years provides cold comfort when measured against the infinite future that heat-death scenarios would allow. Yet the Big Rip scenario reveals something even more disturbing about the nature of reality itself. The destruction wouldn't unfold through familiar processes like explosions, collisions, or gradual decay. Instead, the universe would simply lose the ability to maintain coherent structures as space expands faster than information can travel. Imagine trying to hold a conversation with someone as they're carried away on a cosmic escalator moving at ever-increasing speeds. Eventually, your words can no longer bridge the growing distance, and communication becomes impossible. The Big Rip applies this same principle to every fundamental force in physics. The electromagnetic force binding electrons to atomic nuclei operates through photon exchange across distances measured in billionths of meters. When space expands faster than photons can traverse these microscopic gaps, atoms lose their structural integrity not through violence, but through communication failure. The strong nuclear force faces identical limitations, maintaining proton and neutron binding through gluon exchange across even smaller distances. As cosmic expansion accelerates beyond the speed of information transfer, these fundamental interactions simply cease to function. This communication breakdown creates a universe where physical laws become geographically limited. Different regions of space would experience different physics as expanding distances prevent force-carrying particles from bridging the gaps between matter. A hydrogen atom in one location might maintain its electron-proton bond while an identical atom mere nanometers away loses cohesion entirely, depending on local expansion rates and horizon limitations. Physics itself becomes fragmented and inconsistent across cosmic space. The mathematical elegance of the Big Rip timeline masks the sheer strangeness of this cosmic ending. Unlike heat-death scenarios where entropy gradually increases over astronomical periods, phantom energy creates an active destruction process that accelerates exponentially. The universe doesn't simply run down like a cosmic clock winding towards stillness. Instead, space itself becomes an agent of annihilation, growing more aggressive with each passing moment until it overwhelms every organizing principle in nature. Consider the psychological impact of living through such a scenario. Future civilizations approaching the Big Rip would witness their cosmic environment becoming increasingly hostile as phantom energy grows stronger. Galaxy clusters would visibly separate across the night sky as expansion carries them beyond the cosmological horizon. Individual stars would disappear from view as their light can no longer overcome the stretching of space. The observable universe would shrink dramatically, creating islands of causally connected space that become progressively smaller until entire civilizations find themselves isolated within cosmic bubbles spanning mere light years. Advanced species might attempt technological solutions to survive phantom energy domination. Artificial gravity generators could theoretically maintain planetary cohesion longer than natural gravitational binding allows. Electromagnetic containment fields might preserve atomic structure beyond the point where normal electrostatic forces fail, but these interventions would only delay the inevitable as phantom energy density increases without bound, eventually overwhelming any conceivable technology. The energy requirements for resisting phantom energy effects would grow exponentially as the Big Rip approaches. Maintaining Earth's structural integrity during the final months would require power sources exceeding the total energy output of our Sun. Preserving atomic binding in the last seconds would demand energy densities approaching those found in black hole interiors. No known physics could generate sufficient power to counteract phantom energy's relentless assault on material existence. Recent theoretical work has explored whether consciousness itself could survive the Big Rip through exotic mechanisms that transcend physical substrate requirements. Some proposals suggest that information processing might continue using quantum field fluctuations or gravitational wave patterns that persist even after matter disintegrates. These speculative scenarios invoke concepts from digital physics, where consciousness represents computational processes rather than biological phenomena dependent on chemical reactions within neural networks. However, phantom energy would likely disrupt even these exotic survival mechanisms. Quantum field operations require coherence across microscopic scales that phantom energy would destroy through horizon shrinkage. Gravitational wave communication depends on massive objects accelerating through space, but the Big Rip eliminates all massive structures before reaching its climactic moment. The universe would become truly empty, containing neither matter nor information in any recognizable form. The observational signatures of phantom energy evolution present unique challenges for astronomical detection. Unlike constant dark energy, phantom energy produces time-dependent effects that require measurements spanning billions of years to identify definitively. Current surveys compare cosmic expansion rates across different epochs by observing galaxies at various distances, effectively looking backward through time, as light from distant objects carries information about ancient expansion conditions. These temporal measurements reveal subtle changes in dark energy behavior that accumulate over cosmic history. A universe transitioning toward phantom energy would show specific patterns in how expansion rates evolved, with acceleration increasing more rapidly in recent epochs compared to earlier periods. The dark energy spectroscopic instrument excels at detecting these evolutionary signatures by measuring precise distances to millions of galaxies spanning vast cosmic timeframes. The statistical analysis required to identify phantom energy behavior pushes observational astronomy to its limits. Distinguishing between constant dark energy and evolving phantom energy requires measurement precision better than 1% across cosmic distances exceeding billions of light years. Systematic uncertainties from instrumental calibration, atmospheric effects, and astrophysical contamination must be controlled to unprecedented levels before definitive conclusions become possible. Multiple independent observational techniques provide crucial cross-checks for phantom energy detection. Supernova observations measure luminosity distances through apparent brightness comparisons. Baryon acoustic oscillations reveal angular diameter distances through galaxy clustering patterns. Gravitational lensing effects probe mass distributions through light deflection measurements. Each technique suffers from different systematic biases, making their combination essential for isolating genuine phantom energy signals from observational artifacts. The latest measurements from combining these diverse approaches suggest phantom energy remains statistically viable despite theoretical objections. The equation of state parameter consistently measures slightly below -1 across multiple surveys, though uncertainties prevent definitive conclusions. Future observations will either confirm this trend toward phantom energy or reveal systematic errors that explain apparent deviations from constant dark energy behavior. The implications for fundamental physics extend beyond cosmology into particle physics, quantum field theory, and theories of quantum gravity. Phantom energy violates assumptions underlying the standard model of particle physics, suggesting that our understanding of matter and energy remains incomplete even after decades of experimental verification. The apparent creation of energy from vacuum fluctuations might require modifications to quantum field theory that permit negative energy densities under specific circumstances. String theory proposals offer potential frameworks for understanding phantom energy through higher dimensional physics. These theories suggest that our three-dimensional space represents a lower dimensional surface embedded within higher dimensional structures called branes. Interactions between parallel branes could generate phantom energy effects visible within our dimensional slice while preserving energy conservation across the full higher dimensional space. However, string theory predictions for phantom energy behavior remain highly model-dependent and difficult to test observationally. The theory offers numerous possible compactification schemes for extra dimensions, each producing different phantom energy properties. Without experimental guidance for selecting among these alternatives, string theory provides mathematical frameworks rather than definitive predictions about dark energy evolution. Loop quantum gravity represents another theoretical approach that might accommodate phantom energy through modifications to space-time structure at microscopic scales. This theory suggests that space itself consists of discrete quantum units rather than smooth continuum geometry assumed in general relativity. Phantom energy could emerge from quantum gravitational effects operating at the Planck scale, where classical physics breaks down and quantum mechanics dominates gravitational interactions. The relationship between phantom energy and the multiverse hypothesis adds another layer of complexity to cosmic fate scenarios. Eternal inflation theories propose that our observable universe represents one bubble within an infinite cosmic structure where new space constantly forms through quantum fluctuations. If phantom energy operates within individual bubbles while eternal inflation continues in the larger multiverse, The Big Rip would affect only our local cosmic domain rather than destroying all existence. This possibility offers little comfort for inhabitants of Big Rip universes, as causal isolation prevents communication or travel between different cosmic bubbles. Each universe bubble evolves independently according to its own physical laws and initial conditions. A phantom energy universe would face complete annihilation, regardless of what occurs in neighboring cosmic domains, separated by infinite distances through higher dimensional space. The anthropic principle raises questions about whether conscious observers could exist in phantom energy universes approaching the Big Rip. Complex life requires stable atomic chemistry, planetary environments, and stellar energy sources that phantom energy would eventually destroy. Civilizations might emerge and flourish during early cosmic epochs when phantom energy remains weak, but they would face inevitable extinction as expansion accelerates beyond habitability thresholds. This temporal window for biological evolution creates selection effects that might bias our observations of dark energy properties. If consciousness can only develop in cosmic environments with stable matter configurations, then conscious observers would naturally find themselves in universes where phantom energy hasn't yet reached destructive levels. The apparent fine-tuning of dark energy density might reflect observational selection rather than fundamental physical principles. Current measurements of phantom energy evolution suggest we live during a transitional epoch where dark energy behavior hovers near the critical threshold, separating constant acceleration from runaway expansion. This timing could represent coincidence, fine-tuning, or observational selection effects operating across multiple cosmic realizations. Future observations will determine whether phantom energy represents inevitable cosmic fate or statistical fluctuation within a larger ensemble of possible universes. The technological implications of confirmed phantom energy discovery would revolutionize human civilization's long-term planning strategies. Space exploration programs would face ultimate time limits imposed by accelerating expansion rather than energy or propulsion constraints. Interstellar colonization efforts would need to account for future causal disconnection as expanding space isolates stellar systems beyond communication range. Knowledge preservation becomes critical in phantom energy scenarios where cosmic destruction appears inevitable. Human achievements in science, art, philosophy, and culture would require protection mechanisms that transcend physical substrate limitations. Digital storage systems would eventually fail as phantom energy disrupts electronic components, but information encoding in gravitational wave patterns or quantum field configurations might survive longer than conventional technologies. The search for phantom energy signatures continues accelerating as new surveys come online and existing projects accumulate additional data. Next-generation space telescopes will measure cosmic expansion with unprecedented precision across broader distance ranges and longer temporal baselines. Ground-based facilities equipped with adaptive optics and advanced spectrographs will complement space observations by providing different systematic error patterns and observational strategies. The ultimate resolution of phantom energy questions might require observations spanning several more decades as statistical uncertainties gradually decrease through data accumulation. Current measurements hover tantalizingly close to the phantom energy threshold, but definitive confirmation or refutation demands patience as cosmic surveys methodically map the universe's expansion history across multiple independent techniques and systematic cross-checks. Whether phantom energy represents genuine physics or observational artifact, its investigation continues pushing the boundaries of human knowledge about cosmic fate and fundamental reality. The Big Rip scenario forces confrontation with ultimate questions about existence, consciousness, and meaning within a universe that might actively destroy everything it has created. These cosmic scales dwarf human experience while simultaneously determining the future of every atom, molecule, planet, star, and galaxy that will ever exist. The mathematics describing phantom energy behavior reveals universe evolution toward infinite energy density and expansion rate within finite time periods. This mathematical singularity represents the moment when physical quantities become undefined and classical physics breaks down completely. Beyond the Big Rip lies not empty space or cosmic void, but rather the absence of space itself as the concept of distance loses meaning in infinitely expanding geometry. Human civilization stands at a unique moment in cosmic history where we possess sufficient technology to detect phantom energy signatures while lacking definitive answers about our ultimate fate. Future generations might look back on this epoch as the time when humanity first glimpsed the possibility of universal annihilation through forces beyond imagination. The next decade of observations will determine whether we live in a cosmos destined for gentle cooling or violent disintegration, forever altering our species' perspective on existence within an evolving and potentially hostile universe. The experimental verification of phantom energy behavior requires observational precision that pushes modern astronomy beyond its current technological limits. Each measurement of distant supernovae must account for gravitational lensing effects, dust extinction, and intrinsic brightness variations that could mimic phantom energy signatures. The systematic uncertainties compound across billions of light years, creating measurement challenges that demand revolutionary advances in both instrumentation and analytical techniques. Galaxy redshift surveys face similar obstacles when attempting to trace dark energy evolution across cosmic time. The spectroscopic analysis of millions of galactic targets requires unprecedented calibration accuracy to distinguish genuine phantom energy signals from instrumental drift or atmospheric contamination. Each photon collected by robotic fiber systems carries information spanning billions of years of cosmic history, but extracting reliable dark energy parameters from this ancient light demands statistical methods operating at the very edge of mathematical possibility. The theoretical landscape surrounding phantom energy scenarios reveals fundamental gaps in our understanding of quantum field behavior under extreme conditions. Standard quantum field theory predicts vacuum energy densities that exceed observed dark energy values by factors approaching 120 orders of magnitude. This cosmological constant problem represents one of the most severe theoretical failures in physics, suggesting that our current frameworks miss essential physics operating at cosmic scales. Attempts to resolve this discrepancy through supersymmetry, extra dimensions, or modified gravity theories have produced mathematically elegant proposals but no observational confirmation. The anthropic principle offers one potential explanation, suggesting that we observe precisely the dark energy density required for conscious observers to exist. Universes with stronger dark energy would expand too rapidly for galaxy formation, while weaker dark energy would collapse before stars could ignite. This selection effect might explain apparent fine-tuning without requiring deeper physical principles. However, phantom energy evolution challenges anthropic reasoning by creating time-dependent selection pressures. A universe transitioning from habitable to destructive dark energy behavior would permit biological evolution during early epochs, while guaranteeing extinction during later phases. Conscious observers finding themselves in such cosmic environments would necessarily exist during transitional periods, potentially explaining why current measurements hover near the phantom energy threshold. The multiverse implications of phantom energy scenarios extend beyond simple cosmic bubble formation into questions about the fundamental nature of physical law itself. If different regions of space-time can support different values of fundamental constants, then phantom energy might represent local physics rather than universal behavior. Our observable universe could occupy a cosmic domain where dark energy happens to exhibit phantom characteristics, while neighboring regions follow completely different evolutionary pathways. This possibility transforms the Big Rip from universal catastrophe into local phenomenon affecting only our particular cosmic neighborhood. However, causal isolation between different cosmic domains means that knowledge of alternative physics operating elsewhere provides no practical benefit for avoiding phantom energy destruction within our own region of space-time. The mathematical inevitability of the Big Rip remains unchanged regardless of what occurs in causally disconnected cosmic territories. Advanced civilizations approaching phantom energy domination might attempt exotic survival strategies based on speculative physics beyond current human understanding. Quantum consciousness theories suggest that mental processes might operate independently of biological substrates through information processing mechanisms embedded in space-time geometry itself. These proposals invoke quantum field configurations that could theoretically persist through matter destruction and maintain coherent information patterns across expanding cosmic distances. Alternative survival scenarios involve artificial universe creation through controlled inflation processes that generate pocket universes isolated from phantom energy effects operating in the larger cosmos. Such technologies would require mastery of quantum gravitational phenomena currently beyond theoretical comprehension, but they represent potential escape routes for sufficiently advanced species facing inevitable cosmic destruction. The energy requirements for universe creation would exceed anything achievable through conventional physics, demanding exotic matter sources or higher dimensional energy extraction techniques. The psychological adaptation required for civilizations confronting confirmed phantom energy scenarios would challenge every aspect of cultural development and long-term planning. Knowledge of inevitable universal destruction within finite timeframes would fundamentally alter philosophical frameworks, religious beliefs, and societal priorities across intelligent species. The transition from infinite cosmic future to definite terminal point would force radical reassessment of meaning, purpose, and value within conscious existence. Some civilizations might respond through accelerated technological development aimed at achieving phantom energy resistance or escape mechanisms before cosmic destruction arrives. Others could embrace hedonistic philosophies that maximize immediate experience while ignoring long-term consequences. Religious movements might interpret phantom energy as divine judgment or cosmic purification process, requiring spiritual preparation for transcendence beyond physical existence. The scientific implications of confirmed phantom energy discovery would revolutionize fundamental physics research priorities across multiple disciplines. Particle physics experiments would focus on detecting exotic matter configurations that might produce phantom energy effects under laboratory conditions. Gravitational wave astronomy would search for signatures of space-time modifications that could generate phantom energy behavior through quantum gravitational processes operating at cosmic scales. Theoretical research would concentrate on developing mathematical frameworks capable of describing phantom energy dynamics without violating conservation laws or creating logical paradoxes. These efforts might require abandoning cherished assumptions about space-time continuity, energy conservation, or causal structure that form the foundation of modern physics. The theoretical revolution accompanying phantom energy confirmation would rival the paradigm shifts associated with relativity and quantum mechanics. Observational astronomy would redirect resources toward phantom energy detection and characterization through increasingly sophisticated survey programs. Space-based telescopes optimized for dark energy measurements would map cosmic expansion history with unprecedented precision across multiple independent techniques. Ground-based facilities would complement space observations through gravitational lensing surveys, supernova monitoring programs, and galaxy clustering analysis extending across larger cosmic volumes. The technological spin-offs from phantom energy research could produce unexpected benefits for human civilization, even while confirming our ultimate cosmic fate. Advanced material science might emerge from attempts to create phantom energy-resistant structures. Exotic propulsion systems could develop from research into phantom energy interactions with ordinary matter. Quantum information technologies might arise from studies of information preservation mechanisms operating in expanding space-time geometries. However, these technological advances would operate under the shadow of cosmic mortality imposed by phantom energy domination. Every achievement in science and technology would carry the knowledge that universal destruction awaits regardless of human ingenuity or determination. The timescales involved provide some psychological distance, but the mathematical certainty of cosmic annihilation would color every aspect of future human development. The observational timeline for resolving phantom energy questions extends across the next several decades, as survey precision gradually improves through data accumulation and systematic error reduction. Current measurements require confirmation through independent techniques before phantom energy scenarios can be considered definitive rather than statistical fluctuations within observational uncertainties. The scientific community maintains cautious optimism that improved observations will clarify dark energy behavior within the next decade. Near-term observations will focus on refining equation of state parameter measurements through larger statistical samples and better systematic error control. Long-term programs will trace dark energy evolution across broader temporal baselines by extending observations to higher redshift ranges where cosmic expansion history becomes more clearly distinguishable between different theoretical models. The accumulated evidence will either confirm phantom energy evolution or reveal alternative explanations for apparent deviations from constant dark energy behavior. The philosophical implications of phantom energy scenarios extend beyond scientific speculation into fundamental questions about consciousness, meaning, and value within a finite cosmos. If universal destruction represents inevitable outcome regardless of conscious intervention, then traditional concepts of progress, achievement, and legacy require radical reinterpretation. The apparent purposelessness of cosmic evolution toward annihilation challenges anthropocentric worldviews that assume conscious observers occupy special positions within cosmic development. Alternative philosophical frameworks might emerge that find meaning in temporary existence rather than permanent legacy. Buddhist concepts of impermanence and Hindu cycles of cosmic creation and destruction offer potential models for understanding conscious existence within finite cosmological contexts. Western philosophical traditions emphasizing individual achievement and historical progress would face more severe challenges adapting to phantom energy realities. The search for extraterrestrial intelligence gains additional urgency within phantom energy scenarios, where cosmic communication windows close permanently as expansion accelerates beyond light speed thresholds. Advanced civilizations throughout the galaxy would face similar phantom energy constraints, creating shared existential challenges that transcend species boundaries. Interstellar communication efforts might focus on exchanging knowledge about phantom energy resistance techniques or alternative survival strategies developed by different intelligent species. Contact with alien civilizations could provide crucial information about phantom energy behavior across different cosmic environments and evolutionary timescales. Species that evolved earlier in cosmic history might possess longer observational baselines for detecting dark energy evolution, while civilizations in different galactic regions could experience phantom energy effects under varying astrophysical conditions. This comparative xenobiology would enhance human understanding of phantom energy physics while establishing common ground for interspecies cooperation facing shared cosmic threats. The energy economics of phantom energy resistance would reshape civilization priorities as cosmic destruction approaches. Massive infrastructure projects aimed at preserving human knowledge, culture, and possibly consciousness itself would require resource allocation on scales exceeding current global economic output by orders of magnitude. International cooperation would become essential as individual nations lack sufficient resources to develop phantom energy countermeasures independently. These economic transformations would occur gradually across multiple centuries as phantom energy effects strengthen and cosmic destruction timelines become more precisely defined. Early phases would involve increased funding for fundamental physics research and space-based observation programs. Intermediate stages might feature construction of hardened information storage systems and experimental phantom energy resistance facilities. Final phases would witness desperate attempts at consciousness preservation or universe escape technologies operating at the limits of physical possibility. The biological evolution implications of phantom energy scenarios raise questions about natural selection pressures operating across cosmic timescales. Species that develop spacefaring capabilities might face evolutionary pressures favoring phantom energy resistance or alternative survival mechanisms. However, the timescales involved vastly exceed biological evolution rates, suggesting that technological rather than biological adaptation would determine species' survival prospects. Genetic engineering and artificial life creation might accelerate evolutionary responses to phantom energy threats through directed modification of biological systems. Enhanced radiation resistance, extended lifespan, and improved cognitive capabilities could help engineered organisms survive longer during cosmic destruction phases. Artificial intelligence systems might prove more adaptable to phantom energy environments than biological consciousness, leading to gradual replacement of organic life by synthetic alternatives better suited to cosmic extremes. The mathematical beauty underlying phantom energy physics contrasts starkly with its destructive implications for conscious existence. The equations describing cosmic expansion under phantom energy domination exhibit elegant symmetries and profound connections to fundamental constants governing spacetime geometry. This mathematical elegance suggests that phantom energy represents natural consequence of deeper physical principles rather than arbitrary cosmic accident threatening conscious observers. The aesthetic appreciation of phantom energy mathematics might provide psychological comfort for civilizations facing inevitable cosmic destruction. Understanding the underlying physics that drives universal annihilation could transform terror into appreciation for cosmic processes operating beyond conscious comprehension. The intellectual achievement of deciphering phantom energy behavior would represent triumph of conscious mind over cosmic mystery, even while confirming that consciousness itself faces ultimate defeat. Current observational evidence continues accumulating through multiple independent survey programs operating across different wavelength ranges and cosmic distance scales. Each new measurement adds statistical weight to phantom energy hypotheses while simultaneously revealing additional complexities in dark energy behavior that require theoretical explanation. The observational picture grows more detailed with each passing year, gradually approaching the precision needed for definitive conclusions about cosmic fate. The next phase of phantom energy research will determine whether current hints of evolving dark energy represent genuine physics or systematic errors masquerading as cosmic acceleration changes. Advanced statistical analysis techniques applied to larger datasets will either confirm phantom energy evolution or identify previously unknown sources of observational bias. The scientific community prepares for either outcome while developing theoretical frameworks capable of explaining whatever dark energy behavior future observations reveal. Human civilization stands at the threshold of potentially discovering that our universe faces violent destruction through phantom energy domination operating according to physics beyond current theoretical understanding. This knowledge would transform every aspect of human culture, science, and philosophy while providing unprecedented motivation for technological advancement and interstellar cooperation. The cosmic stakes could not be higher as we await observational resolution of questions that determine the ultimate fate of everything that exists within our observable universe. Whether phantom energy represents genuine threat or observational artifact, its investigation pushes human knowledge toward fundamental limits imposed by cosmic-scale phenomena operating across billions of years of universal evolution. The journey toward understanding phantom energy behavior reveals as much about consciousness and scientific methodology as it does about dark energy physics and cosmic fate scenarios. The detection methods for phantom energy require unprecedented precision across multiple observational techniques that push modern astronomy beyond its current technological boundaries. Scientists must measure cosmic expansion rates with accuracy better than 1% across distances spanning billions of light years, accounting for systematic uncertainties that accumulate like compound interest across cosmic time. Each photon captured by robotic telescopes carries information about dark energy behavior from epochs when the universe was fundamentally different from today, but extracting reliable signals from this ancient light demands statistical analysis operating at the very limits of mathematical possibility. Type Ia supernovae serve as cosmic lighthouses because these stellar explosions achieve remarkably consistent peak brightness regardless of their host galaxy properties. When massive white dwarf stars accumulate matter from companion objects, they trigger thermonuclear detonations that briefly outshine entire galaxies. The physics governing these explosions produces standardized energy outputs that allow astronomers to calculate precise distances by comparing apparent brightness with known intrinsic luminosity. However, phantom energy detection requires measuring tiny deviations in supernova brightness patterns that could easily hide within observational noise or systematic calibration errors. Gravitational lensing effects provide another independent probe of phantom energy behavior through the distortion of spacetime geometry around massive cosmic structures. Galaxy clusters containing thousands of individual galaxies create gravitational fields so intense that they bend light from background objects like cosmic magnifying glasses. The amount of distortion reveals how much invisible dark matter these clusters contain, while subtle changes in lensing strength over cosmic time could indicate phantom energy evolution. but these measurements require exquisite control of atmospheric turbulence, instrumental calibration, and astrophysical contamination sources that threaten to overwhelm genuine phantom energy signals. The baryon acoustic oscillation technique exploits sound waves that propagated through the early universe when space was filled with hot, dense plasma. These acoustic waves left their imprint as subtle correlations in galaxy distributions, creating a standard ruler that appears consistently across cosmic history. Scientists measure this ruler's apparent size at different distances to trace how space has expanded over billions of years. Phantom energy would alter this expansion history in specific ways, but detecting these changes requires mapping millions of galaxies with spectroscopic precision that challenges the limits of current technology. Advanced statistical methods become essential for combining these diverse observational techniques into coherent constraints on phantom energy parameters. Each measurement technique suffers from different systematic biases and error sources, making their combination both powerful and problematic. Bayesian analysis frameworks must account for complex correlations between different datasets while avoiding double-counting information that appears in multiple observational channels. The mathematical machinery required for this analysis operates at the cutting edge of computational statistics and cosmological modeling. Machine learning algorithms increasingly supplement traditional statistical approaches by identifying subtle patterns in cosmic data that human analysis might miss. Neural networks trained on simulated phantom energy universes can recognize characteristic signatures in observational datasets, potentially detecting phantom energy evolution before conventional statistical methods achieve sufficient precision. However, these artificial intelligence systems require careful validation to ensure they discover genuine physics rather than algorithmic artifacts or training set biases. The international collaboration required for phantom energy detection involves thousands of scientists working across dozens of countries and institutions. Major survey projects like the Dark Energy Spectroscopic Instrument represent investments exceeding hundreds of millions of dollars, requiring sustained political and financial support across multiple decades. The scientific infrastructure needed for phantom energy research rivals that of particle physics experiments, but operates across cosmic rather than laboratory scales. Ground-based telescopes equipped with adaptive optics systems compensate for atmospheric turbulence by adjusting mirror shapes thousands of times per second. These technologies allow Earth-based observations to approach the precision of space telescopes while providing much larger collecting areas for faint object detection. However, atmospheric effects create systematic uncertainties that must be carefully modeled and removed before phantom energy signals become visible within observational noise. Space-based observatories avoid atmospheric contamination entirely, but face different challenges from cosmic ray impacts, thermal variations, and mechanical stability requirements. The James Webb Space Telescope and future dark energy missions will provide complementary measurements with different systematic error patterns, allowing cross-validation of phantom energy detection claims. But space missions require decades of development time and face risks of launch failure or on-orbit malfunctions that could delay phantom energy research by entire decades. The observational timeline for resolving phantom energy questions extends across the remainder of this century as survey programs gradually accumulate the statistical power needed for definitive conclusions. Current measurements hover tantalizingly close to the phantom energy threshold, but distinguishing genuine evolution from statistical fluctuations requires patience as cosmic surveys methodically map the universe's expansion history. Each additional year of observations reduces uncertainties and brings scientists closer to understanding whether we live in a universe destined for gentle cooling or catastrophic destruction. Near-term observations focus on refining measurements of the equation of state parameter through larger statistical samples and improved systematic error control. The Dark Energy Spectroscopic Instrument will continue operating for several more years, eventually mapping over 40 million galaxies and quasars across vast cosmic distances. This dataset will represent one of the most comprehensive views of cosmic structure ever assembled, with statistical precision sufficient to detect phantom energy evolution if it operates at currently predicted levels. Next-generation survey programs will extend phantom energy searches to even higher precision through space-based missions optimized specifically for dark energy measurements. These future observatories will combine gravitational lensing, supernova observations, and baryon acoustic oscillation measurements within single integrated platforms. The technological challenges involved in achieving the required precision will drive innovations in detector systems, optical design, and data analysis methods that could benefit numerous other scientific fields. The theoretical interpretation of phantom energy observations requires sophisticated computer simulations that model cosmic evolution across billions of years under different dark energy scenarios. These numerical models must account for complex interactions between dark energy, dark matter, ordinary matter, and radiation while tracking structure formation from quantum fluctuations to galaxy clusters. The computational requirements exceed the capabilities of current supercomputer systems, driving development of new algorithms and hardware architectures optimized for cosmological simulation. Phantom energy simulations reveal unexpected complexities in how cosmic structures respond to accelerating expansion beyond the simple timeline of destruction outlined in analytical models. Galaxy mergers, star formation rates, and black hole growth all exhibit modified behavior in phantom energy universes, creating observational signatures that could provide additional tests of phantom energy hypotheses. These secondary effects might offer earlier detection opportunities than direct expansion rate measurements, potentially resolving phantom energy questions sooner than currently anticipated. The feedback effects between phantom energy and cosmic structure formation create rich phenomenology that challenges theoretical understanding of nonlinear gravitational dynamics. As phantom energy grows stronger, it suppresses the growth of cosmic structure by preventing matter from clumping together under gravitational attraction. This suppression affects galaxy formation rates, cluster assembly, and the cosmic web's evolution in ways that could leave detectable imprints in current observational data. Sophisticated analysis of galaxy clustering patterns might reveal phantom energy signatures hiding within existing survey datasets. Quantum field theory calculations of phantom energy behavior require mathematical techniques that push theoretical physics beyond well-established frameworks. The apparent violation of energy conditions in phantom energy scenarios suggests that conventional quantum field theory might be incomplete or require modifications at cosmic scales. Some theoretical approaches invoke exotic matter configurations with negative energy densities, while others propose modifications to gravity itself that mimic phantom energy behavior through alternative geometric effects. String theory proposals for phantom energy invoke higher dimensional physics where our three-dimensional space represents a surface embedded within larger geometric structures. Interactions between parallel surfaces or branes could generate phantom energy effects visible within our dimensional slice while preserving energy conservation across the full higher dimensional space. However, string theory predictions remain highly model-dependent and difficult to test observationally, providing mathematical frameworks rather than definitive predictions about phantom energy evolution. Loop quantum gravity approaches suggest that spacetime itself might possess discrete quantum structure at microscopic scales, creating modifications to Einstein's general relativity that could produce phantom energy behavior. These theories propose that space consists of quantum units rather than smooth continuous geometry, potentially generating phantom energy through quantum gravitational effects operating at the Planck scale. The observational consequences of these modifications remain largely unexplored, requiring significant theoretical development before experimental tests become possible. The anthropic principle offers potential explanations for why conscious observers might find themselves in universes approaching phantom energy domination. If consciousness can only develop during cosmic epochs, when phantom energy remains weak enough to permit stable atomic chemistry and planetary environments, then intelligent species would naturally observe dark energy behavior near the transition threshold between constant and phantom energy scenarios. This selection effect could explain apparent fine-tuning of dark energy properties without invoking deeper physical principles. However, anthropic reasoning faces challenges from phantom energy evolution because it creates time-dependent selection pressures that vary across cosmic history. Early universe epochs might permit biological evolution under different dark energy conditions than those observed today. The transition from habitable to destructive phantom energy behavior would create observational selection effects that depend on the specific timing of when consciousness emerges relative to phantom energy evolution timescales. Multiverse theories suggest that our observable universe represents one bubble within an infinite cosmic structure where different regions experience different physical laws and fundamental constants. Phantom energy might operate only within our local cosmic domain, while neighboring regions follow completely different evolutionary pathways. This possibility transforms phantom energy from universal catastrophe into local phenomenon affecting only our particular region of space-time. The causal isolation between different cosmic domains means that knowledge of alternative physics operating elsewhere provides no practical benefit for avoiding phantom energy destruction within our own region. The mathematical inevitability of cosmic annihilation remains unchanged regardless of what occurs in causally disconnected territories. Even if infinite numbers of universes avoid phantom energy scenarios, those trapped within phantom energy domains face identical destruction timelines. Eternal inflation models propose that new space constantly forms through quantum fluctuations, creating infinite numbers of observable universe-sized regions within an ever-expanding cosmic structure. Each region would contain its own collection of galaxies, stars, and planets, while potentially following different physical laws determined by random symmetry breaking during inflation. Phantom energy behavior might vary between different inflation bubbles, creating a vast ensemble of cosmic outcomes ranging from gentle heat death to violent big rip scenarios. The probability distribution of different phantom energy behaviors across infinite multiverse realizations remains poorly understood due to fundamental theoretical uncertainties about inflation physics and quantum gravity effects. Some models predict that phantom energy universes represent rare statistical fluctuations, while others suggest they constitute the majority of cosmic realizations. The anthropic principle complicates these probability calculations by introducing observational selection effects that depend on consciousness emergence requirements. Advanced civilizations approaching confirmed phantom energy domination might develop exotic technologies for resisting cosmic destruction through mechanisms that transcend conventional physics. Quantum consciousness theories suggest that mental processes could operate independently of biological substrates through information processing embedded in space-time geometry itself. These speculative proposals invoke quantum field configurations that might theoretically persist through matter destruction, while maintaining coherent patterns across expanding cosmic distances. Artificial universe creation represents another potential escape route for sufficiently advanced species facing inevitable cosmic destruction. Controlled inflation processes might generate pocket universes isolated from phantom energy effects operating in the larger cosmos. Such technologies would require mastery of quantum gravitational phenomena currently beyond theoretical comprehension, but they represent potential survival mechanisms for civilizations willing to abandon their original cosmic domain. The energy requirements for phantom energy resistance or universe creation would exceed anything achievable through conventional physics, demanding exotic matter sources or higher dimensional energy extraction techniques. Some theoretical proposals suggest harvesting energy from black hole rotational mechanics or quantum vacuum fluctuations, but these possibilities remain purely speculative without experimental validation. The technological challenges involved would require scientific advances comparable to the transition from medieval alchemy to modern chemistry. Time travel scenarios offer another exotic possibility for escaping phantom energy destruction by relocating consciousness to earlier cosmic epochs before phantom energy reaches destructive levels. However, causality constraints and grandfather paradox problems make time travel solutions highly problematic, even if the required physics proves feasible. The logical contradictions involved in using future knowledge to prevent future events create theoretical obstacles that might be insurmountable regardless of technological capabilities. Consciousness uploading technologies might preserve mental patterns in substrates more resistant to phantom energy effects than biological neural networks. Digital consciousness operating within quantum computers or exotic matter configurations could theoretically survive longer than organic life as cosmic destruction approaches. However, the fundamental question of whether uploaded consciousness represents genuine continuation of subjective experience or mere simulation remains philosophically contentious and experimentally unanswerable. The psychological adaptation required for civilizations confronting confirmed phantom energy scenarios would fundamentally alter every aspect of cultural development and long-term planning. Knowledge of inevitable universal destruction within finite timeframes would force radical reassessment of meaning, purpose, and value within conscious existence. Traditional concepts of progress, achievement, and legacy would require reinterpretation within cosmic contexts that guarantee eventual annihilation regardless of conscious intervention. Religious and philosophical frameworks would face unprecedented challenges adapting to phantom energy realities that eliminate possibilities of eternal existence or permanent spiritual transcendence. Some belief systems might embrace phantom energy as divine judgment or cosmic purification process, requiring spiritual preparation for transcendence beyond physical existence. Others could reject phantom energy evidence as scientific error or develop new theological interpretations that incorporate cosmic destruction into existing spiritual narratives. Scientific research priorities would shift dramatically toward phantom energy resistance and alternative survival mechanisms as cosmic destruction timelines become more precisely defined. Particle physics experiments would focus on detecting exotic matter configurations that might produce phantom energy effects under laboratory conditions. Gravitational wave astronomy would search for signatures of space-time modifications that could generate phantom energy behavior through quantum gravitational processes operating at cosmic scales. The technological spillovers from phantom energy research could produce unexpected benefits for human civilization, even while confirming ultimate cosmic fate. Advanced materials science might emerge from attempts to create phantom energy-resistant structures. Exotic propulsion systems could develop from research into phantom energy interactions with ordinary matter. Quantum information technologies might arise from studies of information preservation mechanisms operating in expanding space-time geometries. International cooperation would become essential as individual nations lack sufficient resources to develop phantom energy countermeasures independently. The economic transformations required would occur gradually across multiple centuries as phantom energy effects strengthen and cosmic destruction timelines become more precisely defined. Early phases would involve increased funding for fundamental physics research and space-based observation programs, while later stages might feature construction of hardened information storage systems and experimental phantom energy resistance facilities. The search for extraterrestrial intelligence gains additional urgency within phantom energy scenarios where cosmic communication windows close permanently as expansion accelerates beyond light speed thresholds. Advanced civilizations throughout the galaxy would face similar phantom energy constraints, creating shared existential challenges that transcend species boundaries. Interstellar communication efforts might focus on exchanging knowledge about phantom energy resistance techniques or alternative survival strategies developed by different intelligent species. Contact with alien civilizations could provide crucial information about phantom energy behavior across different cosmic environments and evolutionary timescales. Species that evolved earlier in cosmic history might possess longer observational baselines for detecting dark energy evolution, while civilizations in different galactic regions could experience phantom energy effects under varying astrophysical conditions. This comparative analysis would enhance human understanding of phantom energy physics while establishing common ground for interspecies cooperation facing shared cosmic threats. The mathematical elegance underlying phantom energy physics contrasts starkly with its destructive implications for conscious existence. The equations describing cosmic expansion under phantom energy domination exhibit profound connections to fundamental constants governing space-time geometry and quantum field behavior. This mathematical beauty suggests that phantom energy represents natural consequence of deeper physical principles rather than arbitrary cosmic accident threatening conscious observers. Understanding the theoretical frameworks that predict phantom energy evolution reveals the remarkable sophistication of modern cosmological science, while highlighting the limits of human knowledge about ultimate physical reality. The intellectual achievement of developing mathematical models that accurately describe cosmic behavior across billions of years represents triumph of conscious mind over cosmic mystery, even while potentially confirming that consciousness itself faces ultimate defeat through phantom energy domination. Current observational programs continue accumulating evidence through multiple independent techniques that will ultimately resolve questions about phantom energy evolution and cosmic fate scenarios. The next decade of measurements will determine whether apparent hints of evolving dark energy represent genuine physics or systematic errors masquerading as cosmic acceleration changes. Advanced statistical analysis applied to larger datasets will either confirm phantom energy hypotheses or identify previously unknown sources of observational bias that explain apparent deviations from constant dark energy behavior. Human civilization stands at a unique moment in cosmic history where we possess sufficient technology to detect phantom energy signatures while lacking definitive answers about our ultimate fate. The scientific journey toward understanding phantom energy behavior reveals as much about consciousness, scientific methodology, and the limits of human knowledge as it does about dark energy physics and cosmic destruction scenarios. Whether phantom energy represents genuine threat or observational artifact, its investigation pushes human understanding toward fundamental boundaries imposed by cosmic-scale phenomena operating across billions of years of universal evolution. The stakes could not be higher as we await observational resolution of questions that determine the ultimate fate of everything that exists within our observable universe. Each new measurement brings us closer to understanding whether we inhabit a cosmos destined for gentle cooling over astronomical time periods, or violent disintegration through phantom energy effects that will tear apart every atom, molecule, planet, star, and galaxy in existence. The answer to this cosmic question will forever change humanity's perspective on our place within an evolving universe that may prove far more hostile and temporary than we ever dared imagine. The mathematical precision required to distinguish phantom energy from measurement error approaches the absolute limits of what human technology can achieve. Each photon arriving at Earth's telescopes after journeying billions of years through expanding space carries fractional information about dark energy behavior that must be extracted from overwhelming noise contamination. Scientists must measure changes in cosmic expansion rates accurate to FR accounting for systematic uncertainties that accumulate actions of a percent while across distances spanning significant portions of the observable universe. Modern survey telescopes employ thousands of robotic positioning systems that automatically target celestial objects with mechanical precision measured in micro-arc seconds. These automated systems can simultaneously observe hundreds of galaxies per hour, building three-dimensional maps of cosmic structure that extend across 11 billion years of universal history. However, the data quality required for phantom energy detection pushes these instruments beyond their design specifications, demanding calibration accuracy that exceeds anything previously attempted in observational astronomy. Atmospheric turbulence creates fluctuating distortions that blur starlight and contaminate precise measurements needed for dark energy studies. Adaptive optics systems compensate by reshaping telescope mirrors thousands of times per second, but residual atmospheric effects still introduce systematic errors that could easily mask genuine phantom energy signals. Space-based observations avoid atmospheric contamination entirely, but face different challenges from cosmic ray impacts, thermal cycling, and mechanical instabilities that develop over mission lifetimes spanning multiple decades. The statistical analysis required for phantom energy detection involves combining measurements from dozens of different observational techniques, each with unique systematic biases and error characteristics. Supernova brightness measurements must account for dust extinction effects that vary unpredictably between different galactic environments. Galaxy clustering analysis requires modeling complex astrophysical processes that influence how matter distributes itself across cosmic scales. Gravitational lensing observations depend on precise understanding of mass distributions that remain largely invisible to electromagnetic radiation. Advanced computer algorithms process terabytes of observational data through statistical pipelines that operate continuously across multiple supercomputer facilities. Machine learning systems trained on simulated phantom energy universes search for subtle patterns that human analysis might overlook, but these artificial intelligence approaches require careful validation to ensure they discover genuine physics rather than algorithmic artifacts. The computational requirements for phantom energy analysis strain the capabilities of current technology while driving innovations in data processing and pattern recognition. International collaborations spanning dozens of countries coordinate observations across multiple telescope facilities to maximize statistical power and cross-validate results through independent measurement techniques. Scientists share data, analysis software, and theoretical models through collaborative networks that enable rapid progress while ensuring reproducibility of critical findings. However, the complexity of phantom energy research creates opportunities for subtle errors or biases to propagate through multiple analysis chains before detection. Quality control procedures involve extensive cross-checks between different research groups using alternative analysis methods applied to identical datasets. Blind analysis techniques prevent unconscious bias by hiding expected results until statistical analysis reaches completion. Independent replication of key findings using different observational approaches provides additional confidence in phantom energy detection claims, but the time required for these validation procedures could delay definitive conclusions by several years. The observational signatures of phantom energy evolution manifest as tiny deviations from predictions based on constant dark energy behavior. These signals hide within statistical noise that decreases slowly as survey programs accumulate additional data over multiple years of continuous observation. Current measurements suggest phantom energy effects at significance levels approaching but not yet exceeding the threshold for definitive scientific discovery, creating tantalizing hints that require confirmation through extended observational campaigns. Near-term survey programs will refine phantom energy constraints through larger statistical samples and improved systematic error control techniques. The Dark Energy Spectroscopic Instrument continues operating toward its goal of mapping 40 million cosmic objects across vast distances and time periods. This unprecedented dataset will provide statistical precision sufficient to detect phantom energy evolution operating at currently predicted levels, assuming systematic uncertainties can be controlled to required accuracy standards. Next-generation space missions designed specifically for dark energy research will extend phantom energy searches to higher precision through optimized instrumental configurations and observational strategies. These future observatories will integrate multiple measurement techniques within single platforms, enabling simultaneous observations that reduce systematic uncertainties while maximizing statistical power. However, the technological challenges involved in achieving required precision will demand innovations in detector systems, optical design, and spacecraft engineering that push space-based astronomy toward new technological frontiers. Theoretical models of phantom energy behavior require sophisticated numerical simulations that track cosmic evolution across billions of years under different dark energy scenarios. These computational models must account for complex interactions between phantom energy, dark matter, ordinary matter, and radiation while following structure formation from quantum fluctuations during cosmic inflation through galaxy cluster assembly in the present epoch. The numerical algorithms required exceed capabilities of current supercomputer systems, driving development of new computational approaches optimized for cosmological simulation. Phantom energy simulations reveal unexpected complexities in how cosmic structures respond to accelerating expansion beyond simple analytical predictions. Galaxy formation rates, stellar evolution timelines, and black hole growth patterns all exhibit modified behavior in phantom energy universes, creating additional observational signatures that could provide independent tests of phantom energy hypotheses. These secondary effects might offer earlier detection opportunities than direct expansion measurements, potentially resolving cosmic fate questions sooner than currently anticipated. The feedback mechanisms between phantom energy and cosmic structure formation create rich phenomenology that challenges theoretical understanding of gravitational dynamics operating under extreme conditions. As phantom energy strengthens, it suppresses matter clustering by preventing gravitational collapse across increasingly smaller scales. This suppression affects star formation rates and galactic evolution in ways that could leave detectable imprints in current observational data, providing additional avenues for phantom energy investigation. Quantum field theory calculations attempting to explain phantom energy behavior require mathematical techniques that extend beyond well-established theoretical frameworks. The apparent violation of energy conditions suggests that conventional quantum field theory might be incomplete or require fundamental modifications at cosmic scales. Theoretical approaches invoke exotic matter states with negative energy densities, while alternative proposals modify gravitational physics itself to mimic phantom energy effects through geometric mechanisms. String theory models for phantom energy involve higher dimensional physics, where our familiar three-dimensional space represents a surface embedded within larger geometric structures. Interactions between parallel surfaces could generate phantom energy effects visible within our dimensional slice while preserving energy conservation across the full higher dimensional framework. However, string theory predictions remain highly model-dependent and difficult to test observationally, providing mathematical possibilities rather than definitive physical explanations. Loop quantum gravity theories propose that spacetime possesses discrete quantum structure at microscopic scales, potentially generating modifications to Einstein's general relativity that produce phantom energy behavior. These approaches suggest space consists of quantum units rather than smooth continuous geometry, creating phantom energy through quantum gravitational effects operating at the Planck scale. The observational consequences remain largely unexplored, requiring significant theoretical development before experimental tests become feasible. Alternative gravity theories attempt to explain phantom energy effects without invoking exotic matter by modifying gravitational physics itself at cosmic scales. These models propose that Einstein's general relativity requires corrections when applied to distances exceeding billions of light years, creating apparent dark energy effects through geometric modifications rather than additional energy components. However, these theories face challenges in preserving general relativity's remarkable success at smaller scales while explaining cosmic acceleration phenomena. The anthropic principle suggests that conscious observers naturally find themselves in cosmic environments compatible with biological evolution and technological development. If phantom energy evolution prevents stable chemistry during certain cosmic epochs, intelligent species would necessarily emerge during periods when dark energy behavior permits complex structure formation. This selection effect could explain why current observations detect dark energy near the transition threshold between constant and phantom energy scenarios. Multiverse theories transform phantom energy from universal catastrophe into local phenomenon, affecting only specific cosmic domains within an infinite ensemble of possible realities. Different regions of space-time might experience different physical laws and fundamental constants, with phantom energy operating only within particular cosmic bubbles, while neighboring territories follow alternative evolutionary pathways. However, causal isolation between cosmic domains means that knowledge of different physics elsewhere provides no practical benefit for avoiding local phantom energy effects. Eternal inflation models propose continuous space creation through quantum fluctuations that generate infinite numbers of observable universe-sized regions within an ever-expanding cosmic structure. Each inflation bubble could develop unique phantom energy properties determined by random symmetry-breaking processes, creating vast diversity in cosmic fate scenarios across different territorial domains. The probability distribution of phantom energy behavior across infinite multiverse realizations remains poorly understood due to theoretical uncertainties about inflation physics and quantum gravity effects. Advanced civilizations approaching confirmed phantom energy domination might attempt technological solutions for surviving cosmic destruction through exotic mechanisms that transcend conventional physics limitations. Quantum consciousness theories suggest mental processes could operate independently of biological substrates through information processing embedded in space-time geometry itself. These speculative proposals invoke quantum field configurations that might theoretically persist through matter destruction while maintaining coherent patterns across expanding distances. Artificial universe creation represents another potential survival strategy requiring mastery of controlled inflation processes that generate isolated cosmic domains immune to phantom energy effects. Such technologies would demand understanding of quantum gravitational phenomena currently beyond theoretical comprehension, but they represent conceivable escape mechanisms for civilizations willing to abandon their original cosmic territory. The energy requirements would exceed anything achievable through conventional physics, necessitating exotic matter sources or higher dimensional energy extraction techniques. Consciousness preservation technologies might maintain mental patterns in substrates more resistant to phantom energy effects than biological neural networks. Digital consciousness operating within quantum computers or exotic matter configurations could theoretically survive longer than organic life as cosmic destruction approaches. However, fundamental questions about whether uploaded consciousness represents genuine continuation of subjective experience or mere simulation remain philosophically contentious and experimentally unanswerable. The psychological transformation required for civilizations confronting confirmed phantom energy scenarios would fundamentally alter cultural development and long-term planning across every aspect of society. Knowledge of inevitable universal destruction within finite timeframes would force radical reassessment of meaning, purpose, and achievement within conscious existence. Traditional concepts of progress and legacy would require reinterpretation within cosmic contexts that guarantee eventual annihilation regardless of technological advancement or conscious intervention. Religious and philosophical frameworks would face unprecedented challenges, adapt possibilities of eternal existence, or permanent transiting to phantom energy realities that eliminate endance. Some belief systems might interpret phantom energy as divine judgment, requiring spiritual preparation for transcendence beyond physical reality. Others could develop new theological frameworks that incorporate cosmic destruction into existing spiritual narratives, while maintaining hope for consciousness survival through unknown mechanisms. Scientific research priorities would shift toward phantom energy resistance and alternative survival mechanisms as destruction timelines become precisely defined. Particle physics experiments would focus on detecting exotic matter that might produce phantom energy under laboratory conditions. Gravitational wave astronomy would search for space-time modification signatures that could generate phantom energy through quantum gravitational processes operating at cosmic scales. International cooperation would become essential as individual nations lack resources for developing phantom energy countermeasures independently. Economic transformations would occur gradually across centuries as phantom energy effects strengthen and destruction timelines solidify. Early phases would involve increased funding for fundamental physics research and space-based observation programs, while later stages might feature construction of hardened information storage systems and experimental resistance facilities. The search for extraterrestrial intelligence gains critical urgency within phantom energy scenarios where cosmic communication windows close permanently as expansion accelerates beyond light speed thresholds. Advanced civilizations throughout the galaxy would face identical phantom energy constraints, creating shared existential challenges transcending species boundaries. Interstellar communication efforts might focus on exchanging knowledge about resistance techniques or survival strategies developed by different intelligent species facing common cosmic threats. Contact with alien civilizations could provide crucial information about phantom energy behavior across different cosmic environments and evolutionary timescales. Species evolving earlier in cosmic history might possess longer observational baselines for detecting dark energy evolution, while civilizations in different galactic regions could experience phantom energy under varying astrophysical conditions. This comparative analysis would enhance understanding while establishing common ground for interspecies cooperation against shared cosmic destruction. The mathematical elegance underlying phantom energy physics creates striking contrast with its destructive implications for conscious existence. Equations describing cosmic expansion under phantom energy domination exhibit profound connections to fundamental constants governing space-time geometry and quantum field behavior. This mathematical beauty suggests phantom energy represents natural consequence of deeper physical principles rather than arbitrary cosmic accident threatening conscious observers. Current observational programs continue accumulating evidence through multiple independent techniques that will ultimately resolve questions about phantom energy evolution and cosmic fate scenarios. The next decade of measurements will determine whether apparent hints of evolving dark energy represent genuine physics or systematic errors masquerading as cosmic acceleration changes. Advanced statistical analysis applied to expanding datasets will either confirm phantom energy hypotheses or identify previously unknown sources of observational bias. The precision required for definitive phantom energy detection approaches fundamental limits imposed by quantum mechanics and measurement uncertainty principles. Even perfect instruments operating in ideal conditions face theoretical constraints on measurement accuracy that could prevent distinguishing between phantom energy scenarios and alternative explanations for observed cosmic acceleration. These quantum limitations might ultimately determine whether humanity can ever achieve complete certainty about cosmic fate or must accept permanent uncertainty about universal destiny. Future technological developments might overcome current observational limitations through revolutionary advances in detector sensitivity, systematic error control, and data analysis techniques. Quantum sensor technologies could provide measurement precision exceeding classical limits through exploitation of quantum entanglement and superposition effects. Artificial intelligence systems might identify phantom energy signatures invisible to human analysis while controlling systematic biases that currently limit measurement accuracy. The timeline for resolving phantom energy questions extends across several more decades as statistical precision gradually improves through data accumulation and technological advancement. Current measurements hover near phantom energy detection thresholds, but require confirmation through independent techniques before definitive conclusions become scientifically acceptable. The observational evidence will either strengthen toward phantom energy confirmation or reveal alternative explanations that preserve cosmic stability without requiring exotic physics beyond current understanding. Human civilization occupies a unique position in cosmic history where we possess technology sufficient for detecting phantom energy signatures while lacking definitive answers about ultimate cosmic fate. This moment of scientific transition between ignorance and knowledge about universal destiny might represent the most significant epoch in the development of conscious intelligence throughout cosmic history. The implications of phantom energy discovery would forever alter humanity's perspective on existence within an evolving universe that may prove temporary rather than eternal. The investigation of phantom energy scenarios reveals fundamental aspects of scientific methodology, consciousness, and the limits of human knowledge about physical reality operating at cosmic scales. Whether phantom energy represents genuine threat or observational artifact, its study pushes understanding toward boundaries imposed by cosmic phenomena operating across billions of years of universal evolution. The journey toward resolving these questions demonstrates both the remarkable capability of conscious minds to comprehend cosmic mysteries and the humbling recognition that some aspects of reality might transcend the cognitive limitations that evolution imposed on terrestrial intelligence. The mathematical frameworks describing phantom energy evolution operate according to principles that connect microscopic quantum mechanics with macroscopic cosmic geometry through mechanisms that challenge traditional boundaries between different physics disciplines. Understanding how quantum field fluctuations might generate cosmic-scale phantom energy effects requires theoretical synthesis that spans multiple orders of magnitude in distance and energy scales. This intellectual challenge represents one of the most ambitious undertakings in theoretical physics, demanding conceptual advances comparable to those achieved during the development of quantum mechanics and general relativity. The experimental validation of phantom energy theories faces obstacles that extend beyond current technological capabilities into fundamental questions about the nature of scientific knowledge itself. Cosmic-scale phenomena operate across time periods that exceed human civilization timescales by enormous factors, creating observational challenges that might be insurmountable regardless of technological advancement. The verification of phantom energy predictions might require observational programs extending across multiple centuries of continuous measurement and analysis. But even if phantom energy remains forever beyond definitive experimental confirmation, The theoretical investigation of cosmic destruction scenarios provides valuable insights into the fundamental structure of physical reality and the relationship between consciousness and cosmos. The intellectual journey toward understanding phantom energy reveals the remarkable sophistication that conscious intelligence can achieve when confronting mysteries that operate far beyond the evolutionary environment that shaped cognitive capabilities. This achievement represents triumph of mind over cosmic mystery, regardless of whether the ultimate answer confirms or denies the reality of phantom energy domination. The search for phantom energy signatures continues advancing through technological innovation, international collaboration, and theoretical development that pushes human knowledge toward its ultimate boundaries. Each observation, calculation, and conceptual breakthrough brings us closer to understanding whether we inhabit a universe destined for gentle cooling or catastrophic destruction through forces that transcend ordinary physical experience. The resolution of these cosmic questions will determine not only the fate of everything that exists, but also the final assessment of what conscious intelligence can achieve when confronting the deepest mysteries of existence itself. The mathematical singularity that terminates phantom energy universes defies every intuition about physical endings that human experience provides. Unlike explosions that scatter matter across space or collapses that concentrate mass into dense objects, the Big Rip represents a fundamental failure of space and time themselves to maintain coherent structure. The universe doesn't simply end through familiar processes of destruction and decay. Instead, the very framework within which destruction could occur disintegrates beyond recognition. Imagine trying to measure distance with a ruler that stretches faster than you can read its markings. The concept of length becomes meaningless when the measuring device itself expands at rates that overwhelm measurement attempts. Phantom energy creates precisely this situation on cosmic scales where space-time geometry becomes so distorted that physical quantities lose their definitions. Temperature, pressure, density, and even the concept of simultaneity break down completely as expansion rates approach infinity within finite time periods. The horizon problem that plagued early cosmology returns with vengeance in phantom energy scenarios, but operating in reverse temporal direction. Instead of wondering how distant regions achieved thermal equilibrium during cosmic inflation, scientists must confront how previously connected regions become permanently isolated as shrinking horizons prevent any form of causal contact. The universe fragments into causally disconnected domains that shrink continuously until they encompass regions smaller than elementary particles. This causal fragmentation creates a universe where identical physical laws produce completely different outcomes in neighboring regions simply because information cannot travel between them. Two hydrogen atoms separated by distances smaller than atomic nuclei might experience different physics if the cosmological horizon shrinks below nuclear scales. The fundamental forces that govern matter behavior become geographically limited phenomena rather than universal principles operating consistently throughout space. Current theoretical frameworks struggle to describe physics operating under such extreme conditions, where space-time curvature approaches infinite values and particle horizons contract towards zero dimensions. The mathematical tools developed for conventional cosmology assume that space-time maintains sufficient stability to support meaningful calculations about physical processes. Phantom energy scenarios push these assumptions beyond their validity limits into regimes where standard physics becomes undefined. Some theoretical approaches attempt to extend general relativity into phantom energy territory through higher-order derivative terms that might stabilize space-time geometry near singularities. These modifications invoke additional fields or geometric degrees of freedom that could prevent infinite expansion rates while preserving phantom energy's accelerating behavior. However, these proposals remain highly speculative and often introduce new theoretical problems while attempting to solve existing ones. Alternative theoretical frameworks abandon space-time continuity entirely in favor of discrete quantum geometries that might avoid classical singularities through fundamental discreteness at microscopic scales. Loop quantum cosmology suggests that quantum geometric effects could replace the Big Rip singularity with a quantum bounce that transitions into a new cosmic epoch. These scenarios transform cosmic destruction into cosmic renewal, but they require physics beyond current experimental verification. The observational consequences of approaching phantom energy domination would create unprecedented challenges for astronomical measurement and data interpretation. As cosmic horizons shrink, the observable universe would contract dramatically while simultaneously filling with increasingly energetic radiation from accelerated particle interactions. Telescopes would detect rising background radiation levels that eventually overwhelm signals from distant astronomical objects. Galaxy redshift measurements would become impossible as expansion velocities approach infinite values, and wavelength stretching carries electromagnetic radiation beyond detectable frequency ranges. The cosmic microwave background would blue shift into gamma-ray frequencies before disappearing entirely as photon energies exceed measurement capabilities. Astronomical observation would face fundamental limitations imposed by phantom energy effects rather than technological constraints. Gravitational wave detection might provide the final observable signatures of phantom energy domination, as space-time itself oscillates under extreme expansion stresses. These gravitational perturbations could carry information about cosmic destruction processes right up to the moment when space-time geometry becomes undefined. Advanced gravitational wave observatories might detect the universe's final moments through ripples in space-time that propagate faster than matter can respond to phantom energy effects. The biological implications of phantom energy evolution extend beyond simple cosmic destruction into questions about consciousness and information processing under extreme physical conditions. Neural networks require stable atomic chemistry and electromagnetic signal propagation across cellular distances measured in micrometers. As phantom energy strengthens, these biological processes would face disruption long before atoms themselves lose structural integrity. Consciousness might cease functioning when electromagnetic signals can no longer traverse synaptic gaps due to space expansion rates exceeding neural transmission speeds. The human brain contains approximately 100 billion neurons connected through trillions of synapses that require coordinated activity across millisecond timescales. Phantom energy effects could disrupt this coordination by preventing electrical signals from maintaining synchronization across neural networks. Advanced technological civilizations might attempt to preserve consciousness through substrate-independent information processing systems that operate using quantum effects or exotic matter configurations more resistant to phantom energy disruption. These efforts would represent desperate attempts to transcend biological limitations before cosmic destruction eliminates the possibility of conscious experience entirely. Quantum computers utilizing entanglement effects might theoretically continue operating longer than classical systems because quantum correlations transcend space-time separations through non-local connections. However, phantom energy would eventually overcome even quantum entanglement by stretching space faster than quantum information can maintain coherence across expanding distances. The philosophical implications of phantom energy scenarios challenge every framework for understanding meaning and purpose within conscious existence. Traditional concepts of progress and achievement assume that accomplishments can influence future outcomes through causal connections that persist over time. Phantom energy eliminates these causal connections by preventing information transfer across expanding space-time regions. Individual actions lose significance when their consequences cannot propagate beyond shrinking causal domains that eventually contract below molecular scales. Scientific discoveries become meaningless when knowledge cannot transfer between isolated regions of space-time. Artistic creation loses purpose when cultural transmission becomes impossible due to causal disconnection between consciousness and its environment. Some philosophical approaches might find meaning in temporary existence rather than permanent legacy, embracing consciousness as valuable regardless of its ultimate fate within cosmic evolution. Buddhist concepts of impermanence and Hindu cycles of creation and destruction offer potential models for understanding conscious experience within finite cosmological contexts that guarantee eventual annihilation. Alternative philosophical frameworks might emphasize subjective experience over objective achievement, finding value in conscious awareness itself rather than its external consequences. These approaches would treat consciousness as intrinsically meaningful independent of its ability to influence cosmic evolution or preserve information across unlimited time periods. The technological responses to confirmed phantom energy scenarios would reshape civilization priorities as destruction timelines become precisely quantified through improved observations. Massive infrastructure projects aimed at consciousness preservation or resistance would require international cooperation on scales exceeding current global economic capabilities by orders of magnitude. Space-based research facilities might attempt to study phantom energy effects under controlled conditions by creating isolated cosmic domains with modified expansion properties. These experiments would require mastery of inflation physics and quantum gravity that currently exists only in theoretical frameworks without experimental validation. Advanced materials science might develop substances with enhanced resistance to phantom energy effects through exotic matter configurations or higher dimensional geometric properties. However, the energy requirements for creating and maintaining such materials would grow exponentially as phantom energy strengthens toward infinite density values. Information preservation technologies would focus on encoding human knowledge and cultural achievements in formats that might survive longer than conventional storage media. Gravitational wave patterns or quantum field configurations could theoretically maintain information coherence across expanding space-time geometries that destroy ordinary matter-based storage systems. The search for extraterrestrial intelligence would intensify as cosmic communication windows close permanently due to accelerating expansion effects. Advanced civilizations throughout the galaxy would face identical phantom energy constraints, creating shared existential challenges that transcend species differences and technological capabilities. Interstellar archaeological projects might attempt to locate evidence of previous civilizations that developed phantom energy resistance techniques or alternative survival strategies. These investigations would provide crucial information about whether technological solutions exist for conscious beings facing cosmic destruction through phantom energy domination. The mathematical beauty underlying phantom energy physics reveals deep connections between consciousness and cosmos that operate through mechanisms transcending ordinary physical experience. The equations describing cosmic evolution under phantom energy conditions exhibit elegant symmetries and profound relationships to fundamental constants that govern space-time geometry and quantum field behavior. This mathematical elegance suggests that phantom energy represents natural consequence of physical principles operating at the deepest levels of reality rather than arbitrary cosmic accident threatening conscious observers. The intellectual achievement of understanding these principles demonstrates the remarkable capability of conscious intelligence to comprehend phenomena that operate far beyond evolutionary environments that shaped cognitive abilities. Current observational programs approach the precision required for definitive phantom energy detection through technological advances that push measurement capabilities toward fundamental limits imposed by quantum mechanics and cosmic scale phenomena. Each new survey extends statistical power while revealing additional complexities in dark energy behavior that challenge theoretical understanding. The resolution of phantom energy questions will occur within the next several decades as survey precision improves through data accumulation and systematic error reduction techniques. Current measurements suggest phantom energy effects at significance levels approaching, but not yet exceeding thresholds for definitive scientific discovery, creating anticipation throughout the astronomical community. Whether phantom energy represents genuine cosmic threat or observational artifact, its investigation reveals fundamental aspects of scientific methodology and the relationship between consciousness and physical reality. The journey toward understanding phantom energy behavior demonstrates both the remarkable achievements possible through conscious inquiry and the humbling recognition that cosmic mysteries might transcend cognitive limitations imposed by evolutionary history. The implications extend beyond academic curiosity into existential questions about meaning, purpose, and value within a universe that might actively destroy everything it has created. These cosmic considerations challenge anthropocentric worldviews while simultaneously celebrating the intellectual achievements that conscious beings can accomplish when confronting ultimate questions about existence itself. The mathematical frameworks required for phantom energy analysis operate at the intersection of quantum mechanics, general relativity, and cosmology through theoretical synthesis that demands conceptual advances comparable to those achieved during the development of modern physics. Understanding phantom energy behavior requires intellectual tools that span multiple orders of magnitude in distance and energy scales while maintaining mathematical consistency across vastly different physical regimes. The experimental challenges facing phantom energy detection extend beyond current technological capabilities into fundamental questions about scientific knowledge and observational methodology. Cosmic phenomena operating across billions of years create verification challenges that might require observational programs spanning multiple centuries of continuous measurement and analysis. Future technological developments might overcome current limitations through revolutionary advances in quantum sensing, systematic error control, and data analysis techniques that exploit artificial intelligence capabilities for pattern recognition in cosmic datasets. These innovations could provide measurement precision exceeding classical limits while revealing phantom energy signatures invisible to current analysis methods. The timeline for resolving phantom energy questions depends on statistical precision improvements that accumulate slowly through extended observational campaigns and technological advancement. Current evidence hovers near detection thresholds but requires confirmation through independent techniques before definitive conclusions achieve scientific acceptance. Human civilization occupies a unique position in cosmic history where we possess sufficient technology for detecting phantom energy signatures while lacking definitive answers about universal destiny. This scientific transition between ignorance and knowledge about cosmic fate represents one of the most significant epochs in the development of conscious intelligence throughout universal evolution. The investigation of phantom energy scenarios pushes human understanding toward fundamental boundaries imposed by cosmic-scale phenomena, while revealing the remarkable sophistication that conscious minds can achieve when confronting mysteries operating far beyond ordinary experience. Whether phantom energy confirms cosmic destruction or reveals alternative explanations for observed acceleration, its study demonstrates the extraordinary capability of consciousness to comprehend reality across scales that dwarf terrestrial origins. The search for phantom energy continues advancing through international collaboration, technological innovation, and theoretical development that collectively represent humanity's most ambitious attempt to understand cosmic destiny. Each observation, calculation, and conceptual breakthrough brings us closer to determining whether we inhabit a universe destined for gentle cooling or catastrophic annihilation through forces that transcend ordinary physical comprehension. The resolution of these cosmic questions will determine not only the fate of everything that exists within our observable universe, but also provide final assessment of what conscious intelligence can achieve when confronting the deepest mysteries of existence itself. The phantom energy investigation represents the ultimate test of scientific methodology applied to phenomena that operate at the absolute limits of what consciousness can observe, measure, and understand about the cosmic environment that gave rise to awareness itself. The cosmic detective story surrounding phantom energy unfolds through observational techniques that push human ingenuity beyond every previous limit. Scientists must extract signals buried within noise levels that would overwhelm conventional analysis methods, requiring statistical approaches that operate at the absolute boundaries of mathematical possibility. Each photon captured by robotic telescope systems carries fractional information about cosmic expansion that accumulated across billions of years. But isolating genuine phantom energy signatures from contamination sources demands precision that challenges the fundamental limits of measurement science itself. The dark energy spectroscopic instrument represents humanity's most sophisticated attempt to map cosmic destiny through automated observation systems that simultaneously target thousands of celestial objects with mechanical accuracy measured in millionths of an arcsecond. These robotic positioning mechanisms can redirect their focus across vast sky regions within seconds, building three-dimensional reconstructions of universal structure that extend backward through 11 billion years of cosmic history. However, the data quality requirements for phantom energy detection exceed the original design specifications of these instruments, forcing astronomers to develop calibration procedures that approach theoretical limits imposed by quantum measurement uncertainty. Atmospheric disturbances create constantly shifting optical effects that blur starlight and introduce systematic errors capable of masking phantom energy evolution entirely. Advanced correction systems reshape telescope mirrors thousands of times per second to compensate for turbulence, but residual atmospheric contamination still threatens to overwhelm the subtle signals that distinguish phantom energy from constant dark energy behavior. Space-based observations eliminate atmospheric interference completely while introducing different challenges from thermal cycling, cosmic ray bombardment, and mechanical degradation that accumulates over mission durations spanning multiple decades. The statistical machinery required for phantom energy analysis involves combining measurements from dozens of independent observational techniques, each suffering from unique systematic biases and error characteristics that must be modeled with extraordinary precision. Supernova brightness studies must account for dust absorption effects that vary unpredictably between different galactic environments. Galaxy clustering investigations require sophisticated understanding of astrophysical processes that influence matter distribution across cosmic scales. Gravitational lensing observations depend on precise knowledge of mass concentrations that remain largely invisible to electromagnetic detection methods. Modern computational systems process petabytes of cosmic survey data through analysis pipelines that operate continuously across international networks of supercomputer facilities. Machine learning algorithms trained on simulated phantom energy universes search for subtle correlations that human analysis might overlook, but these artificial intelligence approaches require extensive validation procedures to ensure they discover genuine physics rather than computational artifacts. The processing requirements strain current technological capabilities while driving innovations in pattern recognition and distributed computing architectures. International scientific collaborations coordinate observations across multiple continents to maximize statistical power while cross-validating results through independent measurement approaches. Research teams share data, analysis software, and theoretical models through collaborative networks that enable rapid progress while ensuring reproducibility of critical discoveries. However, the complexity of phantom energy investigations creates opportunities for systematic errors or unconscious biases to propagate through multiple analysis chains before detection by quality control procedures. Blind analysis techniques prevent researchers from knowing expected results until statistical calculations reach completion, eliminating unconscious biases that might influence data interpretation. Independent replication of key findings using alternative observational strategies provides additional confidence in phantom energy detection claims. But the time required for these validation processes could delay definitive conclusions by several years. The scientific community balances urgency for understanding cosmic fate against the necessity of maintaining rigorous standards for extraordinary claims about universal destruction. The observational signatures of phantom energy manifest as microscopic deviations from theoretical predictions based on constant dark energy assumptions. These signals remain buried within statistical fluctuations that decrease slowly as survey programs accumulate additional observations over extended time periods. Current measurements suggest phantom energy effects approaching but not yet exceeding the threshold for definitive scientific discovery, creating tantalizing hints that demand confirmation through prolonged observational campaigns. Near-term survey extensions will refine phantom energy constraints through expanded statistical samples and improved systematic error control methodologies. The Dark Energy Spectroscopic Instrument continues operations toward mapping 40 million cosmic objects across unprecedented distance ranges and temporal baselines. This comprehensive dataset will provide statistical precision sufficient for detecting phantom energy evolution operating at currently predicted levels, assuming systematic uncertainties can be controlled to required accuracy standards. Next-generation space missions, optimized specifically for dark energy research, will extend phantom energy investigations to higher precision through integrated observational platforms that combine multiple measurement techniques simultaneously. These future observatories will enable coordinated observations that reduce systematic uncertainties while maximizing statistical sensitivity to phantom energy signatures. However, achieving the required measurement precision will demand technological innovations in detector systems, optical design, and spacecraft engineering that push space-based astronomy toward entirely new performance regimes. Theoretical modeling of phantom energy behavior requires sophisticated numerical simulations that track cosmic evolution across billions of years under different dark energy scenarios. These computational models must incorporate complex interactions between phantom energy, dark matter, ordinary matter, and radiation while following structure formation from quantum fluctuations during cosmic inflation through galaxy cluster assembly in the contemporary universe. The algorithms required exceed capabilities of existing supercomputer systems, necessitating development of new computational methods optimized for cosmological simulation at unprecedented scales. Phantom energy simulations reveal unexpected complexity in how cosmic structures respond to accelerating expansion beyond simple analytical predictions about destruction timelines. Galaxy formation rates, stellar evolution patterns, and black hole growth dynamics all exhibit modified behavior in phantom energy universes, creating additional observational signatures that could provide independent verification of phantom energy hypotheses. These secondary effects might enable earlier detection than direct expansion measurements, potentially resolving cosmic fate questions sooner than current projections anticipate. The feedback processes between phantom energy and cosmic structure formation generate rich phenomenology that challenges theoretical understanding of gravitational dynamics under extreme conditions. As phantom energy strengthens, it suppresses matter clustering by preventing gravitational collapse across progressively smaller scales. This suppression influences star formation rates and galactic evolution through mechanisms that could leave detectable signatures in existing observational datasets, providing alternative approaches for phantom energy investigation. Quantum field theory calculations attempting to explain phantom energy dynamics require mathematical techniques that extend beyond established theoretical frameworks used for conventional cosmological analysis. The apparent violation of energy conditions suggests that standard quantum field theory might need fundamental modifications or extensions when applied to cosmic scales. Theoretical approaches invoke exotic matter configurations with negative energy densities, while alternative proposals modify gravitational physics itself to produce phantom energy effects through purely geometric mechanisms. String theory formulations for phantom energy involve higher dimensional physics, where familiar three-dimensional space represents a surface embedded within more complex geometric structures. Interactions between parallel dimensional surfaces could generate phantom energy effects visible within our spatial slice, while preserving energy conservation across the complete higher dimensional framework. However, string theory predictions remain highly model-dependent and experimentally inaccessible, providing mathematical possibilities rather than definitive physical explanations for phantom energy phenomena. Loop quantum gravity theories propose that space-time possesses discrete quantum structure at microscopic scales, potentially creating modifications to Einstein's general relativity that produce phantom energy behavior through quantum geometric effects. These approaches suggest space consists of fundamental quantum units rather than smooth continuous geometry, generating phantom energy through quantum gravitational processes operating at the Planck scale. The observational consequences remain largely unexplored, requiring substantial theoretical development before experimental verification becomes possible. Alternative gravity theories attempt to explain phantom energy effects without invoking exotic matter by modifying gravitational physics at cosmic scales. These models propose that Einstein's general relativity requires corrections when applied to distances exceeding billions of light years, creating apparent dark energy phenomena through geometric modifications rather than additional energy components. However, these theories face challenges preserving general relativity's remarkable success at smaller scales while explaining cosmic acceleration observations. The anthropic principle suggests conscious observers naturally find themselves in cosmic environments compatible with biological evolution and technological development. If phantom energy evolution prevents stable chemistry during certain cosmic epochs, intelligent species would necessarily emerge during periods when dark energy behavior permits complex structure formation. This selection effect could explain why current observations detect dark energy properties near the transition threshold between constant and phantom energy scenarios. Multiverse theories transform phantom energy from universal catastrophe into localized phenomenon affecting specific cosmic domains within infinite ensembles of possible realities. Different regions of space-time might experience alternative physical laws and fundamental constants, with phantom energy operating only within particular cosmic territories, while neighboring regions follow different evolutionary pathways. However, causal isolation between cosmic domains means knowledge of alternative physics elsewhere provides no practical benefit for avoiding local phantom energy effects. Eternal inflation models propose continuous space creation through quantum fluctuations that generate unlimited numbers of observable universe-sized regions within ever-expanding cosmic structures. Each inflation bubble could develop unique phantom energy properties determined by random symmetry-breaking processes, creating vast diversity in cosmic fate scenarios across different territorial domains. The probability distribution of phantom energy behavior across infinite multiverse realizations remains poorly understood due to theoretical uncertainties about inflation physics and quantum gravity effects. Advanced civilizations approaching confirmed phantom energy domination might develop exotic technologies for surviving cosmic destruction through mechanisms transcending conventional physics limitations. Quantum consciousness theories suggest mental processes could operate independently of biological substrates through information processing embedded in space-time geometry itself. These speculative proposals invoke quantum field configurations that might theoretically persist through matter destruction while maintaining coherent patterns across expanding cosmic distances. Artificial universe creation represents another potential survival strategy requiring mastery of controlled inflation processes that generate isolated cosmic domains immune to phantom energy effects operating in larger territorial contexts. Such technologies would demand understanding of quantum gravitational phenomena currently beyond theoretical comprehension, but they represent conceivable escape mechanisms for civilizations willing to abandon their original cosmic neighborhoods. The energy requirements would exceed anything achievable through conventional physics, necessitating exotic matter sources or higher dimensional energy extraction techniques. Consciousness preservation technologies might maintain mental patterns in substrates more resistant to phantom energy effects than biological neural networks. Digital consciousness operating within quantum computers or exotic matter configurations could theoretically survive longer than organic life as cosmic destruction approaches. However, fundamental questions about whether uploaded consciousness represents genuine continuation of subjective experience or mere simulation remain philosophically contentious and experimentally unanswerable. The universe we inhabit may be far stranger and more temporary than humanity has ever dared imagine. Every observation we've examined, every calculation we've performed, and every theoretical framework we've explored points toward a cosmos balanced on the knife's edge between eternal expansion and catastrophic self-destruction. The phantom energy lurking within dark matter could transform our reality from a stable platform for consciousness into an agent of universal annihilation that tears apart the very fabric of existence itself. Whether the Big Rip represents inevitable cosmic destiny or remains forever beyond the threshold of scientific confirmation, this investigation reveals both the extraordinary power of conscious minds to comprehend mysteries operating across billions of years and the humbling recognition that some aspects of reality may transcend every limitation that evolution imposed on terrestrial intelligence. The next decade of observations will determine whether we inhabit a universe destined for gentle cooling or violent disintegration, forever changing our species' perspective on existence within a cosmos that may prove far more hostile and ephemeral than we ever imagined possible.